So this week we're going to take a look at vectors. As I said, it's 3 sections. The first section will split over 2 days, and then 5-5 will be on Wednesday. And 5-6, I know somebody asked, is there a review day? And I said technically no, but 5-6 is kind of a review because it takes everything we already did in 2D and then does it in 3D. So if you understand how to do everything 2-dimensionally, 3-dimensionally is super easy. Right? So it'll kind of review everything we did earlier in the week. Okay, so first of all, a vector is basically, it's a quantity that models a magnitude and a direction. Magnitude is like speed. So you could think an example of that would be any object that travels. An airplane, throwing a ball. When you throw something, there's a speed to it, and there's a direction you throw it in. When an airplane is flying, there's a compass heading, right? There's a course, and then there's a speed the airplane flies at. So if you wanted to describe the motion of an airplane, you can't just say it's going 500 miles an hour. Well, 500 miles an hour which way? Is it going north, south, east, west? Is it climbing? Is it descending? So we have to describe the direction and the speed. So all those examples I gave you of speed, those are what we call velocity vectors. Another example of a vector is a force. Okay, so if I push down on this table, okay, I'm pushing on it with a certain amount of strength, and I'm also pushing in a certain direction. So if I were to push down on it, but then somebody else were to push up on it, even if we're pushing at the same strength, we're pushing in different directions. Okay? So force has a direction to it and a strength to it, how hard you're pushing. Okay, so those are a couple examples of vectors. At first, we're going to draw vectors. Okay, well, I'll show you how to sketch it as a ray, as an arrow. But eventually, with anything we do in math, sketching gets time-consuming, so we're going to want a faster way to do it. That's just numeric. So we don't have to draw pictures every time we have to solve a problem. Okay, but we'll start by using array. And an array works pretty good if you're going to sketch a picture, because the length of the ray indicates the magnitude. So for example, if you were modeling the speed of something, the longer you make the arrow, that means the faster your object is going. A shorter arrow would mean a slower traveling object. So the length of the arrow represents the magnitude, which again, in the case of a velocity vector, that's the speed. In the case of a force vector, it's how hard you're pushing. And then the way the arrow points, well, that's the direction. So you're pushing to the right, are you pushing left, up, down, which way are you pushing? One thing that can be a little difficult with that is if you really had to draw a very big vector, you could end up with a huge arrow. You might not have enough graph paper, you might not have enough space to do it. So again, that's another disadvantage to drawing. And also, if you're going to draw it, then you need a ruler, because you really want to draw these things straight. Okay. But drawing is a good way to just kind of visualize vectors at first, before we just jump into numbers. All right, so usually when we're talking about a vector, it has 2 points to it. Here and here, P, Q. And if you're starting at P and heading towards Q, you draw it like that. Now, what if you started at Q and headed towards P? Do you think that would be the same vector? Rudy? No, it wouldn't be the same. What would be different? If you start at P and go to Q, or switch it and go the other way. What's different there? Yeah?
The direction.
The direction is different. The magnitude isn't. Because the arrow, the length of the arrow from P to Q or Q to P, it's the same length. But the direction is different. So it is important that we notate correctly. And that's the notation from geometry for array PQ, from P towards Q. We'll shorten that up a little bit. We don't use the geometry notation too much. We usually use a single letter. It's actually a bold letter. But where the array starts, that's called the initial point. Where it ends is the terminal point. Okay, so in this section, there's a ton of vocab stuff. But most of it it's pretty straightforward. Any questions on that? Initial point, terminal point. So I told you we'd have a little bit shorter notation to write vectors. So we can write a vector as a letter with an arrow on top. Okay, that's the symbol for a vector. So you'd pronounce that vector M. And the arrow on top doesn't indicate direction. It's just a little arrow to tell you the M is a vector. Or if you don't want to draw it with an arrow on top, you can make it as a bold letter. Okay, I'm going to try to do my best to make things as bold letters, but it starts to get a little time consuming if I have to make everything bold. So I'll try to be clear when I'm talking about a vector versus just a variable from algebra. But in general, in your book, you're going to see vectors as bold letters. Same thing on the test. The vectors will be in bold. I think people use bold because it's a little easier on a computer than trying to put an arrow above a letter. You can do it, but bold is quicker. All right, so one thing we're going to look at is how we can take vectors and combine them. Okay, we'll start by taking vectors and adding them. All right, first of all, I just kind of want to think, logically what would happen here. So let's think of vector as a force. Okay. So let's say that I'm pulling in the direction of up on this table with 30 newtons of force. That's how you can measure force. So I'm pulling up with 30 newtons. Somebody else is pulling up with another 30 newtons. What's going to happen if we both do that at the same time? I pull up with 30 newtons. Somebody else pulls up with 30 newtons. Let's start with the direction. What would be the direction of our combined forces? It would be up. We're both pulling up, so we're working together. And what would be the strength of the pull? 60. So when you take two vectors, whether it's a force vector or a velocity vector, and combine them, you get a new vector. Sometimes it's a new direction, and sometimes it's a new amount of force. If I was pulling up on the table with 30 newtons, and somebody else was pushing exactly down on the table with 30 newtons, well, what would happen there is our forces would cancel out. The direction, essentially, there wouldn't be a direction, because there wouldn't be a force anymore. Right? It's balanced. Right? So when you take two vectors and combine them, you get a new vector. Okay? Same thing would work for velocity. If you were, say, driving 30 miles an hour in your car, and then all of a sudden the wind came behind you, and the wind was coming at a certain speed and it pushed you. Think of the wind as wind has direction, and the wind could be blowing at a certain speed. Well, if you're driving and then the wind pushes you, now you're going to go even faster. Right? And maybe the wind could push you off track. Think of an airplane. Right? If you're flying south and the wind is blowing from the west, well, now the wind is going to blow you in a new direction. It's going to blow you off course. Okay? But the point is you're going to have a new course. You'll have a new direction to your airplane, and you're going to be going at a different speed. Okay, a headwind, we'll talk about that, would slow a plane down, versus a tailwind that would push the plane along and speed it up. All right, so we're going to look at the two vectors v and w, okay, and I'm going to show you how you add them together. Okay, I'm going to show you kind of a simple way, quick, with an example, and then I'll write it all out. But the idea is, let's say the black arrow was a force and the red arrow was a force, and I want to combine them. Well, if you want to add the black one onto the red one, you line them up so that the ending point of the one in red and the beginning point of the one in black are right on top of each other. Okay, so think of that, maybe that red arrow is an airplane. Think of that black arrow as the wind. And I want to know what's going to happen when the wind interacts with the airplane. Well, the airplane, first of all, is going to go a lot faster because the wind is blowing it roughly in the direction it wants to go. But it's also going to blow it off course a little bit. So that arrow that I just drew would represent combining the airplane and the wind. It has a new direction, and it's much longer. It has a new speed. Right, so I'll explain how I just did that. So you're going to line up the vectors so that the ending point of the first vector is right on top of the starting point of the next vector. Just like that. Okay, so you line them up just like that, and then visually, how do you get the new answer? Well, you end up connecting like a diagonal from where you start to where you finish, just like that. Okay, so the combined vector, or the new vector that you get, is found by connecting the initial point of where you started to the ending point of where you finished. Whether they're called v and w or whatever letters they use. Okay, and you can do this with more than just two vectors. Let's say you had one like this, one like that, and one like that. And you wanted to know what would be the effect if you combined all those vectors together. Well, you just stack them all together and see if they're not grouped. So that would be the effect of combining two of them. And then that's the third one. So if I wanted to know what would be the overall effect, connect where you started, follow the path of the arrows to where you finished, and now connect it. So that would be the effect if you combine all those vectors together. Think of that as maybe wind blowing. Okay? If you had wind blowing in those three directions, and you like let a paper airplane go, that's the way it would go. With all the wind combining. Any questions on that? Okay. So some of the notes, it's going to be kind of hard to get it exactly to the same scale that I have, but just estimate it the best you can. So we've got two vectors. We're going to add them together. Right. So Peter, can you tell me how I would line these vectors up so I can add them together?
the initial point of W on the terminal point of Z, or V.
Exactly. Put the initial point of W on the terminal point of V. And now what would the last step be? And now what's the last step?
You trace the initial point of V to the terminal point of W.
Yeah. Connect what I have in red. And what I just drew in red, that's the vector V plus W. It's bold. And that's it. It's V plus W. Okay, let's look at this one. Before I line them up and add them, does anybody have a thought what's going to happen here? Yeah? Yeah, they cancel out. Because if you want to add V to W, you're going to take the ending point of V, okay, which I'll mark in red, and you're going to line it up with the beginning point of W, which I'll mark that in red. All right, so now let me put a green dot there and there. So once I line up the red dots, then I'm going to connect the starting point of V, which is in green, to the ending point of W, which is in green. Okay, so line up the red dots first, and then connect the green ones. Okay. Let's just grab that. So I'm going to line up the red dots. I'm not even looking at what's going to happen. Just line up the red dots. And now if I connect the green dots, they're the same dot. So what did I say happens whenever you combine two vectors? What do you always get? You get a new vector. You don't get a number. So the answer here is called the zero vector. So you can make it bold. We could write it that way. The zero vector is the only vector that doesn't have a direction because it doesn't have any length to it. Okay, so if that was a multiple choice question and let's say 0, the number was listed as a choice, and 0, the vector was listed, the answer here is the zero vector. Combined vectors, always get a vector. Okay, I'll talk more about the zero vector later, but for now. Okay, vector addition is commutative and associative. Okay, I'll show you that it's commutative. I'm not going to show you it's associative. Does anybody remember what commutative means? Think of like, we say addition is commutative, so is multiplication. What does that mean? Yeah?
Combination.
What do you mean it's a combination?
Combining.
Okay, it involves combining two things. And when you would add, does the order matter when you combine things? No. 2 plus 6, 6 plus 2, same thing. Well, it works with vectors too. If you find V plus W or W plus V, just how you're lining them up on paper, you're going to get the same result. So this is kind of hard to write in your notes because I'm going to move things around, but if you just have the formula, that's good enough. All right, so let's do V plus W first. That means I'm going to take V and put W on the end of it. That's V plus W, and let's write the answer. I'm just going to put that off to the side. So that's V plus W. And again, these are bold. Now I'm going to switch it around. I'm going to take W and I'm going to add V. Okay, so I took W first and then I put V on the end of it. Well, if I just take what I just had, you can see I get exactly the same thing. So the point here is if you're adding vectors visually, you can add them together in any order you want. The only thing that's important is when you connect them, all the arrows should go the same way. So like if you were adding another vector onto this, maybe it would be there, there, and there. If you follow the path of the arrows, they all go the same way. You would not ever want to line vectors up like that. There's something wrong there. Okay. So you always line up one end that has an arrow to one end that doesn't, not two ends that have arrows. Okay. Any questions on that? Okay, so that shows that it's commutative. And it's also associative. I'm not going to go through and show it, but associative doesn't have to do with the order. It has to do with grouping, because the order is the same on each side. ABC, ABC. That part's the same. But it's just which one did you do first? Well, think of it with numbers. If you want to do 1 plus 2 plus 3, well, if you add 1 and 2 first, you get 3 plus 3 is 6. Or if you add 2 and 3 first, you get 5 plus 1 is still 6. So the point here is the order that you add vectors, it doesn't matter. And to show that, I'd have to go through and do it with 3 vectors, but I'm not going to show it. Any question on the idea? Vector addition is associative and commutative. Okay, so we talked about that already. If you add a vector and its opposite, you get the 0 vector. What's the difference between this and that if you drew them on paper? There's something that's the same about them, but then there's something that's different. What's different?
The direction.
The direction is different. In fact, it's exactly opposite directions. Think of it as 180 degrees rotated. But what's the same?
The length.
The length, right? The magnitude of these arrows would be the same. That's what we just said. So the difference is the direction they point, but they have the same magnitude. Any question on that idea? So the first part of this section is very visual. Okay, it's lots of drawing stuff. When we start the second half, and towards the end of the first half, that's when we get into more numeric stuff. Okay? Drawing is okay, but when you get to even when you get to 3D, then drawing becomes a lot harder. Okay? All these principles I'm showing you, the way you could stack vectors together, you can do it in 3D, but now you'd probably want to use a computer to visualize it. For 3D, it's kind of nice if you can have like a model in front of you, like on a screen, that you can rotate it and look at it from different angles. But 2D, you don't really need that. All right, so if we can do addition, we can also do subtraction. And the way we're going to think of subtraction is same way you can do it with numbers. If you're not sure what it means to do 2 minus 3, but you know what it means to do addition, especially addition with negative numbers, just think of it this way. Instead of subtracting 3, just add the opposite. Adding the opposite is subtraction. So that's how we're going to subtract vectors. In order to do subtraction, we will add the opposite. Okay, what does it mean to find the opposite? We just talked about that. Opposite just means it points the other way. That's all. Okay, let's try an example with subtraction. V minus W. Before I do it, can somebody tell me how I can rewrite that so I can think of it as addition instead of subtraction? Yep.
V plus negative W.
right, so we've got V, right, and I've got that right there. There's V, plus negative W. Now, Alex, you said negative W. I don't have that drawn, so how would I get negative W from W? Yeah.
You switch the direction 180 degrees.
Yeah, I can just take and rotate it 180 degrees, which geometrically is the same as doing a horizontal reflection and then a vertical reflection. Now I have negative W, and now I'm going to add this to that. That's how you do subtraction. So take V and put negative W on the end of it. And then, Connor, how do I get my final answer now? It's set up, but what do I have to do?
Just measure the distance.
Right, connect from here to there. And there's your answer. That's V minus W. Okay, so subtraction, super easy. All you gotta do is take the regular vector, rotate it, flip it around 180 degrees. Any questions on that? Okay, so it's adding, subtracting, scaling. Anyone have a guess what it means to scale a vector? Think about like if you build a scale model of something. What is that? Yep.
A smaller version.
A smaller version, right? Smaller, or I guess scale could even be larger. Maybe if you were building a model of like the cell, you might make it on a shoebox, or sometimes they do something like that. It's a larger scale model. But the point of a scalar is when you multiply a number, like 2, and a vector. 2, V. Okay, that's called a scalar product, because you're multiplying a number by a vector. Now, notice here I said number and vector. We have not talked about, and we're not going to do it today, how do you multiply a vector times a vector? That's different. Okay. This is a vector times a number. That's a little easier to do. Vector times a vector doesn't come up until Wednesday. But the point is, when you scale a vector, you get a new vector. It could be longer, or it could be shorter. There's actually a third thing that can happen. Anybody know what else could happen besides the vector getting longer or shorter? Yep.
Change direction.
You could do one very specific direction change. How could you change the direction?
Exact opposite.
Right, you could make it point exactly the opposite by putting in a negative. That's the only direction change you can do. You can't just turn it any way you want, but you can flip it around completely by putting in a negative. So a scalar can shorten, lengthen, or reverse the direction of a vector. Okay, so let's practice with a vector V, just a vector that points to the right. And I want to find 2V and a half V. So Eric, what's 2V going to be? How do you think 2V is going to compare to 1V? Okay, can you be more specific?
2 times as big.
2 times as big? How about the direction?
It's going to be the same.
It's going to be exactly the same. V versus 2V, there's no change in direction. In fact, it's very easy to, even on paper, to get 2V. All you have to do is take V, make a copy of it, make another copy of it, and stack them together. There's V plus V. Now you have 2 of them. And draw your final answer. Okay, so there's 2v. Robin, how about a half v?
Reduce the direction, shorten out.
It's going to shorten it. How about the direction?
Direction would stay the same.
Direction stays the same. For half v, just estimate it, roughly where you think a half would be. If you were doing it on graph paper, you could measure it more accurately. Any question on that one? All right. Okay, so we have v, and now they want negative 1v. Okay, we've kind of already done that. I didn't tell you it was a scalar product when we did it, just putting a negative in front, but that's all that's really happening here. So Irene, what's going to happen with v compared to negative 1v? Do you know what's going to stay the same? There's something there that won't change.
The direction.
Not the direction. The direction's going to change. So it's the length that stays the same. Someone else tell me how the direction is going to change. Yep.
We're going the opposite direction.
Right. It's going to point, and I'm just going to sketch it by hand. Okay. If the negative wasn't there, all you'd have is a 1. Right? That doesn't change the length at all. That doesn't do anything. So the length isn't changing. But then once you put a negative in front, flips the direction. And negative 1/3 v, well, we've already got the negative from the last problem. It's pointing the other way. So now just make it 1/3 as long. So maybe about like that. And there's negative 1/3 v. Okay, so when you have a negative number in front of a vector, it does 2 things. 1, changes the direction. 2, it lengthens or shortens. In this case, it shortened. Any question on that one? Right. In this one, we can kind of combine both ideas. We're going to find 2 scalar products and then add them together. So Emily, what's the first thing they're asking me for here to add?
2.
They're asking for 2v. So I'm going to find that first. So I'll take a copy of v and another copy of v. There's 2v. And now, Heidi, what am I adding on to the end of that? So we have 2v, but what do they want me to add to it? Well, what does it say? Find 2v plus 3 w's. So take w and put 3 of them. This is where it requires a little bit of thinking ahead because you don't want to go off the edge of your page. And I think I'm going to be okay. If I had to do like 6w, then I definitely would be running out of space. So there's 2v plus 3w. And now, Zach, what do I do to get my final answer?
Just kind of make a point at the end of that one, and then the other end,
Yep.
and then just connect them.
Yeah, and then just connect them with as straight of a line as you can. So the answer here, and on some problems in the homework, is a picture. That's all you have to do. Any questions on that? All right. Okay, so if you see this symbol, these double bars around a vector, that means they want the magnitude. So in other words, they're asking for a number. how long is the vector. For now, I'm not going to tell you how to find the length, but I'm just going to tell you what the symbol is for it. Okay, double bars. And magnitude is always positive, because magnitude is a length. Okay, anytime you measure length, it's not negative. Okay, so I want you to compare those two vectors. One on the left says magnitude of the vector x. The one on the right is the magnitude of the vector negative x. Anybody tell me how those two things would compare to each other? Emma?
Their lengths would be the same.
They're the same. Magnitude of x, magnitude of negative x. That's like saying distance from here to Boston, distance from Boston to here. It doesn't matter what direction you're traveling. Those two quantities are the same. Right. If the magnitude is equal to 1, you happen to measure a vector and it comes out to exactly 1 unit. There's a special name for it. Did anybody remember the type of circle we studied that had a radius of 1? What was that circle called?
Unit circle.
Unit circle. So what do you think the vector's called that comes out 1 unit long? Unit vector. Yep. Okay, so unit vector, just a fancy way to say I have a vector that's 1 unit long. That's all. Okay, so another term. How people doing with all the different terms? Any questions so far? Okay, we're going a little bit quicker than normal. And we're almost done the first half of the section. Okay, if there are any, just let me know and we'll slow down. All right, so now we're getting towards the end of the first part of 5.4, and I told you at that point, we're going to kind of get away from drawing. Okay, because drawing is great, but if you really want to start doing things with vectors more efficiently, quicker, we're going to have a different way to write vectors. So there's actually 2 ways we can write vectors besides drawing an arrow. One way is used more than the other, but I'm going to show you both. The first way in your book, they refer to it as what's called an algebraic vector. And the way you write an algebraic vector is kind of like a coordinate, but instead of using parentheses, you use these angled brackets. If you accidentally put parentheses, then it would be wrong because that's a coordinate. Okay, so you've got to put these angled brackets. And then inside the angle brackets, there's 2 numbers. Okay, I've called them A and B. Does everybody have what's above algebraic vector so I could scroll up? Okay. And I've labeled the A and the B as the horizontal and the vertical. And you might be like, well, what's that mean? Well, if you think of a vector like that, that vector actually has 2 directions to it. If you ask me what way is it pointing, I would say it's pointing up and to the right. So, how much to the right is it pointing? About that much. How much up is it pointing? About that much. Right and up. There's 2 directions to it. That's what the A and the B represent. That's called the horizontal component of the vector. That's the part that's going right. That's the vertical component of the vector. That's the up part. So vertical part can be up or down. Horizontal part could be left or right. And when we describe it, we're going to have numbers. So like if this was on a grid, I could just count 1, 2, 3, 4, 5 units right, or 1, 2, 3 units up. That's it. So we just could count. So let's say I had the vector 3, comma 4. What that means is from somewhere. Okay, start anywhere you want. Doesn't tell you where to start. Do I have a grid? No. Let me just make kind of a quick grid. I'll start from the origin. You don't have to, but if you do start from the origin, you would go 3 units to the right, 1, 2, 3, 4 units up, 1, 2, 3, 4. That point right there is where my vector would end. And I said, start from the origin and end right there. That's the vector 3, comma 4. So start from an initial point. But what this notation does not tell you is where to start. You want to start from the origin? Great. You want to start somewhere else? That's fine too. Just start somewhere. From that point, go left or right, depending on if A is positive or negative. And then go up or down, depending on whether B is positive or negative. So think of A and B as directions from how you get where you started to where you're going to finish. Okay, let's do another one. Let's do -2, 5. All right, so from a starting point, let's start here. No, let's not start there. Let's give myself more room. Let's start there. What direction am I going to go first? Yep.
2 to the left.
2 to the left, and then
5 up.
5 up. 2 to the left, 5 up. That is the vector, -2, 5. This is also the vector -2, 5. 2 to the left, 5 up. The notation does not tell you where to start, but where do you think the most common place to start is? Where do you think most vectors start from? The origin, yeah. Most of the time, you want to start at the origin. And if a vector starts at the origin, another vocab word, it's called a position vector. So a lot of times what we want to do is they'll give you a vector that's not a position vector, and you're going to convert it into a position vector. Okay, so I'll use the grid up above to do that. Okay, so a vector that has its initial point at the origin, that's a position vector. Okay, let's to keep the arithmetic easy, let's start here, end here. You don't need a grid for this, but if you just label it on paper with the coordinates correctly, that's all you're going to need. Make it a little bigger so people could see it. Rudy, what's the coordinates of my initial point? Over 3, yeah. And up 2. And again, that's not a vector. That's why I put parentheses. It's just a coordinate. Just labeling the initial point And then the terminal point, 3, 4, 5, 6, 7, go over 8, up 4. Okay. So now, keep those two coordinates in mind. Let's look at what happens if I move just the vector to the origin. Okay. And I'm going to keep, you know what, I'm just going to rewrite it. Initial point was 3, 2. Terminal was, what was it? 8, 4. Okay, so this was what we started with. Okay. Now, I'm going to move it, and it's going to end up somewhere else, and I want you to tell me where it is now. So I'm going to erase this so it's not confusing. Where's my starting point now? Yep, Alex?
The origin, 0, 0.
Origin. And where's my ending point? 5, 2. Yep. So terminal 5, 2. Now, did anybody see some arithmetic that you can do with these numbers to get those numbers? Yeah?
8 minus 4 and 4 minus 2.
Yeah, you subtract them. And you have to do it in that order. Terminal minus initial. 8 minus 3 gave me my terminal, 5. 4 minus 2 gave me my other terminal coordinate, 2. So, if you're given a vector, and it has 2 points, an initial point and a terminal point, and they want you to find a position vector. In other words, tell me where the vector would be if you moved it to the origin. All you have to do is subtract the points. And I'm going to write that next. Okay, so in the box, that's the formula to find a position vector. Terminal minus initial for the x's, comma, terminal minus initial for the y's. And if you ever forget that, you could always just go back to what we did. Take a piece of graph paper and move the vector yourself on the graph paper and see where it ends up. But that's where it's always going to end up. Any question before we try one of those? All right, let's look at the last example here. Find the position vector. So we got the point -1, 2. You've got the point 4, 6. So take a second on your own. See if you can plug those 2 points into the formula and find the position vector. If they don't tell you which one is initial and which one is terminal, assume P1, 1 is initial, P2 is the next one, that's terminal. All right, so first, you don't have to give me the final answer, but can someone just give me the calculation for the x coordinate? I'm going to subtract what minus what? Yep.
-1 minus 4.
All right, so let's double check. So position vector, terminal minus initial. Scroll down. Which one is the terminal x value here?
So it'd be 4 minus 3.
Yes. So terminal minus initial. And now for my y value, what would I put there?
X minus 2. I mean 6 minus 2.
6 minus 2. Okay, and now simplify. So the final answer is going to be 5, 4. Hey, anybody get 5, 4 for the vector? Yep. So if you wanted to draw that vector, you start at the origin, you go 5 units right, 4 units up. What would happen if you switch the initial and the terminal point?
The wrong answer.
You get the wrong answer, yes. And what would be wrong about it? It would actually be something that's right if you were to draw it, but then there'd be something that's wrong. Yeah? The direction would be reversed. If you switch initial and terminal, your vector would point exactly the wrong way. Be the right length, wrong direction. Okay, so any questions on that? All right. So as far as the homework part, that's where it's going to stop. I'm going to do a little bit of 5.4 part 2 because tomorrow we're going to lose 45 minutes. But I think if we cover about 20 minutes now and 20 minutes tomorrow, we'll get most of it in. Okay, so hopefully you kind of find this easier than trig identities because it's a lot less abstract. It's more visual. And now in this section, a lot more numerical. Anybody like trig identities better? You do? Yeah. Yeah, some people like them because if you don't like calculations, then you're not really into this stuff. The trig identities is definitely, it's more abstract, and some people like them. All right, so same section. Okay, the next thing they mention is what does it mean for two vectors to be equal? It doesn't mean that they're drawn in the same spot. If I take that and make a copy of it, those two vectors are equal. Are their initial points and terminal points the same? No. They have totally different initial coordinates and terminal coordinates. But their components are the same. They each have the same horizontal and the same vertical component. The way I could tell is I could just line them up. They're identical copies. Okay. So I just want to stress the idea that for vectors to be equal, it does not mean the initial coordinates and terminal coordinates are the same. It means the components are the same. Any question on that? Not a huge idea. We're not really going to spend any more time on it. That's all I'm going to say about that. All right, so the last way that I'm going to show you how to work with vectors this week, and this is the way that we're going to use for pretty much everything from this point forward. Bless you. Okay, we're not really going to be doing sketching anymore. We're not going to use the angle brackets too much. Bless you. Although we'll practice with angle brackets because it is good to know it. But the last way we're going to look at is what's called unit vector notation. Okay, as I said, by far this is the most common way to work with vectors. Can someone remind me again, what is a unit vector? Alex?
Vector that equals 1.
It's just a vector that has a length of 1. So I'm going to show you two special unit vectors. And these letters that I'm showing you, think of them as reserved letters. You would never use this letter for anything else because it already has a meaning. Okay, don't ever name a vector I. Okay, ever. It's like using pi as a variable. Not a good idea. It already stands for something else. Okay. I is a unit vector that points 1 unit to the right. That's all. So what does it look like? It looks just like that. It's a unit vector, and it points 1 unit to the right. j is a unit vector. So it's 1 unit long, and it points up. And there's a picture of what j would look like. It's a unit vector. It points 1 unit up. Now, what you basically do to do this final notation is think about stacking together combinations of i's and j's to get where you want to go. If you want to end up over here and start here, you want to think about how many i's you would need to stack together to get to that point, and then how many j's you would need. And and I'll explain how you write the final answer. Okay, well, we'll go through and do one. Probably not that number, but I'll do one in a second. Okay, so we're going to use I and j to build vectors. Okay, think of I and j as like building blocks. Okay, so there's pictures of I and j. So let's take the vector 3, 4, and I'm going to show you how you can write it in unit vector notation. Which number, the 3 or the 4, represents the horizontal? The 3. Okay, so I'm going to start from the origin. You don't have to, but that's probably the best place to start. I need 3 of the horizontal. What was the name of the horizontal again? What did we call that vector? I. So I need, I'll put it off the grid. I need 3 of the I vectors. Okay, so start with that. So I'm going to make some copies. And now I'm going to stack them all together. 1, 2, 3. So that's 3i. Now I'm going to add something onto the end of that. What number represents the vertical there? Yeah?
4.
4. And when we write using a unit vector, what was the name of the vector that pointed up? Yep? J. So I need 4 of the j's. So now stack those together. Okay, so I've got 4 of them drawn. So I got 1, 2, 3, 4. So what I've just drawn right there, using addition, which again, we're not really going to be drawing it again, just the first time to show you, is 3 i's plus 4 j's. In green, that is the vector 3i plus 4j. So to take something written with the angle brackets and write it with I and j, basically just take away the comma, take away the angle brackets, put an I with the 3 plus, and then a 4 with the j. Right, so how would you write something like -2, 7? How would you write that in our new notation? Yeah?
Go left 2, left 7.
Okay, so that's how you would sketch it, but how would you write it?
Oh. Would it just be the same with the letters? 2i, 7j, plus 7j.
Plus 7j. Algebraic vector, unit vector notation. So even though I points to the right and j points up, you might think, well, doesn't that limit me to only being stuck in the first quadrant? Nope, not if you make I and j negative. If If you make I and j negative, then you can go left and you can go down instead of always going right and up. Any question on that? All right, so I think what I'll do is I'll give you the formulas for vectors. We'll maybe try a couple examples, and then we'll stop with the formulas. So what the formulas allow us to do is add, subtract, and scale vectors without drawing pictures. So now we can get away from the sketching idea. To match up with what your book does, they use v and w for the names of the two vectors in the formulas, and they use alpha as a scalar. Remember, a scalar is just a number. 2, 3.5, just a number. Okay, my two vectors, v has a horizontal component x1, vertical y1. W, horizontal component x2, vertical y2. If you want to add two vectors together, instead of taking where one of them ends and the other one starts and then lining them up on graph paper and drawing in a diagonal, to add them together with numbers, all you have to do is add the horizontal components, those are the x's, comma, and add the vertical components, and that's a y. And you can do this whether it's in algebraic vector form or unit vector form. It's easier for me to write the formula like this. But we'll practice writing the answer with the i's and j's and without it. Okay, to subtract two vectors. On paper, if you want to do it visually, you've got to take the second vector, flip it around, and then add it. Well, with numbers, you don't have to do any of that. Numbers, just subtract the x's, subtract the y's. Okay, for a scalar, okay, this would be like 2v or 3v, okay, something like that. Think of that scalar as a distributive property. You multiply each component by what you're scaling. So if you wanted to take the vector 5, 3 and double it, it would become the vector 10, 6. Just multiply the number to each component. Okay, and the last formula, and then we'll do an example, is how to find the magnitude. So I showed you this symbol earlier, but I said I'm going to hold off on telling you how to calculate it. That's how you calculate it. Does that formula kind of look like anything else from geometry? Anybody recognize it? Something squared plus something squared and then take the square root? It's the Pythagorean theorem. And the reason is, think about if you had a vector, and I said to you, find the length of that arrow. Well, that's the vertical. That's the horizontal. It's basically you're just finding the hypotenuse of a triangle. Square it, add them up and take the square root. So finding the length of a vector is using the Pythagorean theorem. That's all. Okay, so we'll try one of each example, and then that'll be a good place to stop. All right, so I've got two vectors. I wrote them for you both ways. Vector v is 2i plus 3j. Vector w is 3i minus 4j. Okay, first thing I want to do is add them. Let's put the answer with i's and j's first. Okay, so vector v, the horizontal component is 2. Vector w, the horizontal component is 3. What would you get when you combine the 2i and the 3i? 5i, yep. 5i. And now what about when you combine 3j and negative 4j? Negative 1j, yep. Do you have to put the negative 1 in front of the j? No. You got to put the negative, but you don't have to put the 1. Can someone tell me how you would write it in that notation? Yep.
Just 5, 1.
5, negative 1. Now, you do have to put the negative 1 if you're going to write it that way. Okay. So adding vectors that way, it's a lot faster than using graph paper. Okay. Subtract. Mason, could you tell me what I would get for my I component, my horizontal, if I subtract v and w? Yep, negative 1i, or you could just put negative I. And how about your j component? Good. 3 minus negative 4 becomes 3 plus 4. So we get negative I plus 7j. Or Katie, if I wrote it the other way, how would I write it?
I don't know.
Not sure? Well, what number is in front of I? Negative 1. And what number is in front of j?
7.
7. That's it. 3v. Anyone think they could tell me what 3v would be? Cameron?
6i plus 9j.
Yeah. You're tripling the vector v, so triple each component. Triple the 2, triple the 3. 6i plus 9j. Or in the other notation, 6 comma 9. And last one is finding the length. Magnitude of v. What's the first thing you have to start with when you find the magnitude? It should all be under a what symbol? Yeah,
Square root.
should all be under a square root. Square the x component, square the y component, add them up. 2 squared gives me how much? 4? Plus 3 squared gives me 9. And what's 4 plus 9? 13. Is that answer a vector? No, that's a magnitude, that's a number. Every other answer we did was a vector. When you add vectors, you get a vector. When you subtract, you get a vector. When you scale, you get a vector. When you find the length, you don't. You get 13 inches, feet, whatever it is. Okay, so we covered a lot of stuff here. Yes, square root of 13, right?
Yeah.
Thank you. Square root of 13. And that's it. Okay, so the second half, I'm going to save that homework for tomorrow. We probably have about 20, 25 minutes left, so we'll see if we can finish it tomorrow. And then the homework for tonight is page 344. Number 1, 8 to 22 even, and 26 to 32 even. I think on 26 to 32, the directions in the book, they ask you to do a couple things. I'm just asking you to find the position vector. That's all you have to do.